This is the introduction to section 2.6, which is implicit differentiation. So the first example is going to look very similar to things we've already done. Find the slope of the tangent line to xy equals 16 at x equals 2. So in order to do that with the techniques we've learned previously, we would have to solve for y. So y is 16x to the negative first power. We can use the power rule to find the derivative of y with respect to x, which is negative 16x to the negative 2, or negative 16 over x squared. And then the slope of the tangent is just dy dx at x equals 2. So that would be negative 16 over 2 squared, or negative 4. Okay, that example, there's no reason to handle that one any other way. But just as a tool to introduce the idea of implicit differentiation, I'm going to use this example. And so we're going to look again at xy equals 16. And we are going to assume y is some function of x. Say f of x. Okay, so I'm going to rewrite this as x times f of x is equal to 16. And now I'm going to take derivatives with respect to x on both sides of the equal sign. Okay, to do that on the left-hand side of the equal sign, we will need the product rule. So we take the first function, which is x, times the derivative of the second. Well, I don't know what f of x is, but I know how to notate its derivative. It's f prime of x, plus the derivative of x, which is 1, times the second function, which is f of x. And that is equal to the derivative of 16 with respect to x, and the derivative of 16 is 0. So right here was the product rule. Okay, and what did we want to find? Well, we were asked to find the slope of the tangent line at 2. So we want to find f prime of 2. Okay, well, let's go here. Everywhere we see an x, let's replace it with a 2. We know 2 times f prime of 2 plus f of 2 is equal to 0. So if we knew what f of 2 was, we could get our hands on f prime of 2, and f of 2 is really the y value when x is equal to 2. Okay, so let's come up here, right above this. When x is equal to 2, 2 times f of 2 is equal to 16. So f of 2 is equal to 8. Okay, and once we have that information, we can finish. 2 times f prime of 2 plus we just decided f of 2 is 8. And if we solve this for f prime of 2, we get negative 8 divided by 2, or negative 4, which is the same thing we got as the slope of the tangent line above. Now you may watch me do that and go, well, why would we ever do that when this doing this explicitly is much more straightforward? I agree, but the point is to illustrate this idea of implicit differentiation, because it will come in handy in situations like this one. So here's some curve. It's given by 2x squared plus 3y cubed equals 5xy. And I want us to find the equation of the tangent line at the point 1, 1. Okay, 1, 1 is a point on this curve, because that would say that 2 plus 3 is equal to 5, which is a fact. And so, but unlike the situation above, we cannot solve for y explicitly unless we have a computer algebra system, but we can still find the derivative. Okay, and so let's find that derivative 2 ways. Really, we're going to find it the same both ways, but 2 different notations. So the first way is let's let y, so we're assuming implicitly that y is some function of x. So we get 2x squared plus 3 times f of x, sorry about that, 3 times f of x cubed is equal to 5x times f of x. I'll show you the, I don't know if I'm going to have room here, so I'll show you the other notation down below. All right, and so now we're going to take derivatives. With respect to x. Okay, on both sides of the equal sign. Okay, so the derivative of 2x squared, 4x squared. The derivative of 3f of x cubed. Okay, the 3 comes down. We use the power rule. It's 9 times f of x squared, but since that isn't just an x inside, we have to use the chain rule. So that is times f prime of x. Okay, and then on the right-hand side, we're going to use the product rule. So we get 5x f prime of x. Let me move this. Plus, derivative of 5x is 5 f of x. Okay, let me make a notation of what we used here. We just took the derivative of 2x squared. Here we used the chain rule. And here we used the product rule. Okay, we've been asked to find the equation of the tangent line here at 1, 1. So that means when x is 1 and when f of x is 1. And so let's do that. Everywhere we see an x, let's replace it with a 1. So we get 4 times 1 squared plus 9 times f of 1 squared plus f prime of 1 equals 5 times 1 times f prime of 1 plus 5 times f of 1. And up here, 1 f of 1 tells us that f of 1 is equal to 1. So now we can simplify even further. We get 4 times 1 is 4. If f of 1, everywhere I see an f of 1, this is a 1, this is a 1. So I get 9 times 1 squared times f prime of 1, which is 9 times f prime of 1. Whoops, what happened here? There is a sign error. Sorry, that should not have been a plus. It should have been multiplication all the way. So we get 9 f prime of 1 is equal to 5 times f prime of 1 plus 5. All right, let's see. We bring 5f prime of 1s over to the left-hand side of the equal sign, and we have 4 times f prime of 1 is equal to 1. So f prime of 1 is equal to 1/4. Now we already have everything we need to write the equation of this tangent line. We have our point, which is 1, 1. We have our slope, which is 1/4. And the tangent line is y minus 1 is equal to 1/4 times x minus 1. Okay, that works. Every time you need this implicit differentiation technique, you can replace y with f of x, but the notation gets a little bit cumbersome. So I'm going to change the notation a little bit down here. Down here, every time I need to take a derivative of y, I'm going to notate it with a y prime. So here, instead of f of x and f prime of x, use y and y prime. Okay, let's do that here. So we're going to start with sine of x plus y is equal to 2x minus 2y. And we want to find the tangent and the normal line at the point pi comma pi. Okay, so again, take derivatives, the first step. With respect to x. Okay, the derivative of sine of anything is cosine of that thing, but because the thing inside parentheses is not just x, I'm going to need the chain rule. So I'm going to get cosine of x plus y times the derivative of x plus y. The derivative of x is 1, and the derivative of y is y prime, is equal to, on the right-hand side, the derivative of 2x is 2, and the derivative of 2y is 2 times y prime. Okay, and so now we want the slope of the tangent line at the point pi, pi. So everywhere we see an x and a y, we're going to replace those with pi and pi, and our job is to get our hands on y prime, because that is the slope of the tangent line. So we get cosine of pi plus pi times 1 plus y prime, what we're trying to solve for, is equal to 2 minus 2 copies of y prime. So that is cosine of 2 pi. Cosine of 2 pi is the same thing as cosine of 0, so that is 1. So this term is 1, and so we are left with 1 plus y prime is equal to 2 minus 2y primes. Let's see, if I bring 2y prime to the left-hand side of the equal sign, I'm going to have 3y prime. Sorry about that. And I bring a 1 to the right-hand side of the equal sign. 2 minus 1 is 1. So we get y prime equals 1/3, and that was at the point pi, comma pi. Great, we have a point and a slope, and so we can write down the equation of the tangent line using those. Tangent line looks like y minus pi is equal to 1/3 times x minus pi. Okay, now we need to remember we are also asked about the normal line, and the normal line is the line perpendicular to the tangent. So the normal line is perpendicular to the tangent, so its slope, we'll call y prime again, is the negative reciprocal of 1/3. It's -3, and it also goes through the point pi, comma pi. So that tangent line is y minus pi equals -3 times x minus pi. Okay, see if you can use this information to tackle the activity for section 2.6, and I would try to rely on this kind of shorthand notation here from the second example, but if you want to do the first few with the f of x and f prime of x notation, there's certainly nothing wrong with that.